Hello everyone, welcome back to my channel and to episode 6 of Statistics for Machine Learning series. So far, we have covered why machine learning needs statistics, descriptive statistics, data distributions and outliers, correlation versus causation, and sampling and bias. You can see each of these episodes in the Statistics for Machine Learning course, which is a playlist on my YouTube channel. So without further ado, let's get started on today's episode. Have you ever built a model that was perfect on training data but failed on new data? That's not magic, that's statistics. Today we'll uncover one of the most important ideas in machine learning, the bias-variance trade-off. Once you get this, you'll finally understand why models overfit, underfit, and how to balance them. Let's first set this stage. When we train a model, we're trying to find a function that captures the pattern in our data. But there is a problem. The data itself always contains noise. If our model is too simple, it misses the real pattern. It's underfitting. If it's too complex, it starts memorizing the noise. It's overfitting. So how can we tell what's happening statistically? Let's break it down. In statistics, we describe these problems using two concepts, bias and variance. Bias means your model makes the same kind of mistakes consistently. It's too rigid. And variance means your model's predictions jump around wildly when the data changes. It's too sensitive. Now, let's put this into perspective with an example. Imagine we're predicting exam scores based on study hours. If we fit a straight line, the model might be too simple, it underfits, and if we fit a 10th degree polynomial, it memorizes the sample, so it overfits. But the perfect model lies somewhere in between these two. Let's see what happens when we measure model errors by a simpler example. Imagine you're drawing dots on a line, you have some dots on paper, that's your data, and then you try to draw a line or curve that goes through them. That's your model. At first, you draw a straight line. It doesn't fit all the dots perfectly. It misses some, right? That's called high bias. Your line is too simple, so it doesn't learn the real pattern well. But if you draw it again with new dots, it'll look almost the same. So the model is very stable. Variance is low. Now, you use a very twisty line that goes through every single dot perfectly. As you can see, it fits this data really well, and bias goes down, which is good. But next time you get new dots, your twisty line won't fit them well. That's because it also learned the noise and mistakes from the old dots. That means variance goes up, and your model became unstable. So the total mistake your model makes is made of 3 parts. Bias to the power of 2 plus variance plus noise. Bias is error from being too simple, variance is error from being too wiggly, and noise is random stuff you can't fix anyway. When you make the model a little bit more complex, it learns better. It means that bias goes down, but then it starts overfitting, which means that variance goes up. At first, total error gets smaller, but after a point, total errors starts getting bigger again. So you need to stop at the bottom of the valley of the slope where the total error is smallest. In other words, the goal isn't to make bias 0 or variance 0. It's to find the sweet spot where their sum, total error, is smallest. That's where the model learns the main patterns, low bias, but doesn't overreact to noise, low variance. If I want to give you a tangible analogy, I would say think of a dartboard. High bias and low variance means all darts hit the same wrong spot, consistent but inaccurate. And low bias and high variance means darts scatter all over, sometimes right and mostly random. And good model is when darts cluster around the bullseye and balance between accuracy and consistency. So now that we know what each of them means, let's see how we can fix this in practice in an ML model. To handle bias and variance, we use smart statistical tricks. We use cross-validation to estimate real errors, We use regularization to penalize complexity, and we use simpler models or more data to stabilize learning. Cross-validation is when we test the model on different parts of the data to see how well it works on new data. This helps find out if it's overfitting or not, if it has too high variance or not. Regularization means we tell the model, don't be too complicated, and it adds a small penalty when the model has too many wiggly parts, so it keeps the variance low. And a simpler model or more examples helps the model learn the real pattern instead of random noise, which reduces variance and bias together. So next time your model performs weirdly, you'll know exactly which side of the trade-off you're on and what to do to fix it. In the next episode, we'll explore another hidden factor that affects models, scaling and normalization. If you like this video, don't forget to subscribe to catch up on the next episodes of this series. See you in the next one.